Welcome back. In this lecture, we will revisit two dominant operational variables that determine the performance of a fuel cell. The two dominant variables are temperature of the fuel cell and the composition of the reactants that are fed into the fuel cell. We are already seen that the potential delivered by a fuel cell can be expressed in the following manner. This is the open circuit potential. These are the surface or activation potential of anode and cathode. This is a concentration or transport over potential from anode or cathode. This is the ohmic over potential. So typically, when temperature increases, we had already seen that equilibrium thermodynamics suggests that the potential, the open circuit potential, decreases. However, with an increase in temperature, these over potential, that is the activation over potential, decreases a lot more. And in some ways, especially in SOFC, the ohmic potential also decreases significantly with increase in temperature. Therefore, even though this looks like a disadvantage, the decrease in over potential with increase in temperature is a big advantage. Therefore, typically at higher temperature, you would get higher potential from the fuel cell, and therefore you have an efficient fuel cell. Moving on. So we had seen that the ohmic over potential, it can be expressed in this manner. Conductivity of the electrolyte has a complex temperature dependence. But in some cases, it can easily be rationalized, especially, for example, in an SOFC, solid oxide fuel cell, the presence of lattice, okay, so with, let's say, discrete translation symmetry, makes it easier to think through conductivity of the anions. Typically, the conductivity depends upon vacancy. So when an anion moves, a vacancy in this direction, the vacancy would move in this direction. So when you have such a movement of vacancy or an anion, the potential energy surface is typically expressed in this following manner. So what is important to understand is this is an activated process. As anion moves or the vacancy moves the opposite direction, there is change in coordination, and because of which there is a transition state whose energy is greater than these 2 points. So this activation energy for ion hopping will determine the temperature dependence. So typically, the conductivity would increase with temperature because this is a constant. As T increases, the rate of ion hopping will also increase. Therefore, the conductivity increases. So this is a reasonable model, especially when a solid lattice is present. But in general, even in a liquid state electrolyte, uh, the diffusion is an activated process. Therefore, increasing the temperature would increase the transport. So overall expectation is that the ohmic loss decreases with increase in temperature. However, pressure does not have a significant effect. The way to think about that is when you apply pressure, there are small changes in bond distances, which does not significantly affect the energetics. So when we move on to the activation potential, first you should clearly understand what exactly we mean by activation over potential that is elaborated in this lecture. So the important point is that this is also an activated process. This was elaborated in this lecture. So this is an activated process when, let's say, a reduction is occurring. So this reactants can go to the products, and the products can revert back to these reactants. So because it's an activated process, we can again think through something like an Arrhenius relationship. The rate of forward reaction and the rate of backward reaction in this case is a measure of exchange current density, because these processes are activated, we can still write a temperature dependence in this form. The central message is that as the temperature increases, the activation barrier can be crossed more frequently. Therefore, the exchange current density also increases with temperature. This is the main part. So in this way, it is used as soon as the exchange current density increases, the activation over potential also decreases with increase in temperature. So the moving on from temperature to composition, we had looked at the compositional dependence of the exchange current density. Most of the time, we are looking at a multi-step, multi-electron transfer reaction. So these coefficients, which are elaborated in this lecture, have to be obtained from experiments. So these exponents are determined experimentally. It's not very easy to derive these exponents from simple microkinetic models. So this is the way it is done in practice. That is, you measure, you take some data, and from that data, you can recover the exponents. So what is important to understand is between these two reactions, we have already stated that this is much more challenging reaction. The O potentials associated with oxygen reduction reaction is much higher. This, because of this fact, a lot more emphasis on electrocatalysis of oxygen reduction reaction has been explored. Typically, hydrogen oxidation reaction is the easier reaction. Moving on to concentration over potential, we have already covered the fundamentals of concentration over potentials in these two lectures. You must have a good understanding of the content of these lectures to think through the concentration over potential. So the central quantity here is the limiting current density. So the limiting current density can be expressed in this manner. This is the diffusion coefficient, the concentration of the relevant species. This is the mass transfer boundary layer thickness. So if you have, because you have the gas phase reactant, concentration can be converted in terms of pressure, and you get this form. So what you want to do is to increase the limiting current density. So let's see the functional form of limiting current density. Here, the temperature comes at the denominator, so which seems to suggest that the limiting current density will decrease with increase in temperature. But let's elaborate further. As the pressure increases, the concentration also increases. Therefore, limiting current density increases. But temperature is also, diffusion coefficient is also a temperature dependent quantity. And diffusion increases in a nonlinear manner with temperature. So that increase in diffusion coefficient compensate for the presence of temperature at this in the denominator. So overall, the limiting current density increases with temperature. So it is advantageous to have higher temperature of operation. All these things are summarized in this table. So please go pause and go through this. So this gives you a consolidated summary of all the different parameters that go into rationalizing the fuel cell behavior. This has been covered over 3 lectures, but this is a good summary table. What we have not addressed are material specific features. What we have addressed are some general physicochemical features that can be rationalized from general arguments from electrochemical thermodynamics, kinetics, and transport, but very specific material parameters have not been looked at. So, in is more specifically, even though we may claim that we can have better performance at higher temperature, other challenges like material degradation and corrosion um, have a debilitating effect at higher temperature. So this aspect of uh, corrosion and other material challenges have not been discussed, and because one of the reason is that they are fairly specific. Okay, there are no general argument. You have to look at a specific case and try to understand what's going on. In the next lecture, we will look at an important topic, which is how to get what determines uh, maximum power from a fuel cell. Thank you.